European Union projects on quality culture and institutional review. He was the supervisor in 3 European Union student projects. He also took part in 17 scientific research projects from TÜBİTAK, Turkish Scientific Research Council, and Uludağ University. He organized 8 international congresses and workshops. He also has been in the scientific committees of over 30 international congresses. To his credit, he has published 49 books and 200 scientific research papers, and half of them which are in SCI and Web of Science database. He has received the award, the name as the highest number of annual publications in 2011 and 2013. The special prize, Bolgono Coordination Committee member in 2011, the highest number of annual projects in 2012, Scientist of the Year in 2012, the annual Successful Academic Group in 2012, and the Best Performance Award in 2016 in Uludağ University. He is working as an editor in 21 international scientific journals and referee for more than 100 journals. He is a member of 6 international and national mathematical societies. One of knowledge is having the right answer. Intelligence
Thank you, Satish. Hi, welcome to Orhan. Okay. First of all, fourth ICCSPAM in a row, and inviting me again, even online. I would like to be there physically in Kongunado Arts and Science College, the beautiful place, to see Madam Vasuki, my friends, Mohana Priya, Venkatachalam, Ravi, all the others, the head of departments, the friends, even the friends in the library. I made many friends there. It's a beautiful place. Next year, I hope to be there physically. So today, let's go to mathematics now. I will talk about some works I did with my students in the last year, 2020. It was a bad year because of COVID, and we were stuck in our houses. That made us work harder and produce harder, probably. I don't know. At least for me, it was like that. So this is one of the problems I studied last year. It is about graphs obtained by sequences, number sequences. Not any sequence. You can apply the idea to any sequence, actually. At the end of the talk, you will have some ideas, I hope. But the 3 sequences, special sequences, we applied are Fibonacci numbers, Fibonacci numbers, and Lucas numbers. Of course, there are millions of number sequences, and you can apply the same methods to those sequences to produce new graph classes. I shall illustrate only the Fibonacci graphs, but Lucas graphs and Fibonacci graphs are there, published. I will give you the references. You can search for them. You can find them freely in the internet, or you can ask me. I can send you if you cannot find. and you can apply the same method to obtain these graph classes. So, in summary, we defined some number with my student, with my PhD student, who he has finished now last year, I think. He defined together with me a characteristic number, like Euler characteristics. In topology, you know very well that Euler characteristic is very important. It's a real characteristic. It's one of the most well-known mathematical characteristic numbers. So our number omega, it's denoted by omega, is related to this Euler characteristics, and it is also related to the number of faces. Okay, this is called in graph theory cyclomatic number, because of the cycle. You count the cycles in the graph. It helps this number, this characteristic number, helps us for a given degree sequence. I will talk about this. We obtain some realizations of this degree sequence. You are given some positive numbers, positive integers, 1, 2, 2, 2, 3, 3, 3, 4, 4, like this. And you want to construct a graph having vertex degrees equal to these numbers, these integers, okay? That's the idea. If you can do this, then the graph is called the realization of this degree sequence, of this set, okay? So we studied many problems, many extremal problems, many normal problems, many equalities, inequalities, combinatorial, structural, topological properties of the graphs, realized graphs for a given degree sequence. Briefly, we have shown that if omega is less than or equal to -4, this is something to calculate, you will see, then the graph is certainly disconnected. For example, this was an open question. Given a degree sequence, like the one I gave 1 minute ago, there are realizations, maybe millions of them, maybe 3, 4, 5, I don't know, depending on the size of the degree sequence. Are they connected? Are these realization connected? Disconnected? Some of them connected, some of them disconnected. We don't know. We didn't know about this. So now you calculate this number, and if it's less than or equal to -4, then all the realizations will be disconnected. You cannot have a connected realization. That's the idea, okay? If omega is -2, that's a special case, very special case, and the graph is connected, if you want it to be connected, then the graph is certainly acyclic. It's a tree, okay? Connected and acyclic. If omega is non-negative, then the graph is connected, and the graph is connected, then the graph is certainly cyclic, okay? We have given an algorithm for realizing a given degree sequence in those 3 cases above. Omega is less than or equal to -4, omega is -2, and omega is non-negative, okay? These are 3 important classes for our work. This number, omega, helps to decide whether possible realizations are connected, disconnected, or both, as I said. It helps to decide whether D is forcibly or potentially connected. You may not know about forcibly or potentially connectedness. These are adjectives, forcibly or potentially. If you use it with some idea like connectedness, compactness, openness, closedness, like this, okay? Forcibly means all of them must be having this property. Potentially means there is at least one with this property. Potentially connected means there are lots of realizations. At least one of them has the potential to be connected, okay? The others may be disconnected, doesn't matter. But in forcibly connected, all of them must be, it's forced, okay? It helps to decide whether the possible realizations are cyclic or acyclic or both. It helps to decide the realizability of the given degree sequence, usually denoted by D or DS. It helps to find the number of phases of a connected realization. It helps to compare the number of components of a realization with M and N, the order and the size of the realization. There are lots of things I can write now. This is a list I prepared some years ago, one and a half years ago. So there are many more to say. You see some of them. I will not read all of them. It helps to calculate the topological indices, for example. At least you can get bounds for the topological indices, which is also important, because many graph theorists now, many chemists work on topological graph indices nowadays. This number omega helps to calculate maximum and minimum domination numbers. Very important idea in graph theory and applications. It is related to cyclomatic number, Euler characteristics, many things, and it helps to determine the number of phases, components. Yes, for example, in a minute we shall see, for example, for a given degree sequence, if it is connected, if any one of these realizations is connected, then the minimum number of components would be 1, because it's connected, it's one piece, it's all in one piece. But what is the maximum number of components, pieces, okay, disconnected pieces of the graph realizations? What is the maximum number? Can you draw this set, okay, as a graph in maximum 20 ways, for example, 20 pieces? We don't know, but now we can say that with omega, with the help of omega. All right. Yeah, there are many other things you can see, but I will give you more concrete examples in my talk, so I will skip that part. Okay. If you write me, I can send you this talk and the related papers by email. Okay. In 18th century, this is the motivation for our study. Euler realized that for any drawing consisting of vertices and lines on a compact orientable surface, we have this number n minus n plus r is fixed. It's very interesting. N, M, and R denotes the number of vertices, edges, and faces, okay? N is usually used for the number of vertices, the order. M is the size, the number of edges, and R is the number of faces. For example, in a tree, there is no face, so R is 0, okay? So this number is fixed for compact orientable surfaces. What is a compact orientable surface? For example, the sphere. Sphere is one example. It has no holes. It's like a dough. Okay, you can play with it. In topology, you know, you can stretch things, you can push things in. So you can do anything without deleting them, without taking them apart. Okay. So sphere is the most easy compact orientable surface. What is the second one? Taurus, like a donut, sweet donut, okay? Double donut, like eyeglasses with 2 holes, without glasses, of course. These kind of things are compact orientable surfaces. All right. I will give you 2 examples. This is for spherical or at the same time planar graphs. What is common in the 7 graphs you see at the screen? You see n minus m plus r in all of them is equal to 2. You can check any one of them. For example, the last one at the right end, bottom end, okay? There are 5 vertices 5 vertices, 1, 2, 3, 4, 5, 6 edges, and 1, 2, and outside. In topology, you count the outside face as well. In graph theory, we don't do this. Okay. So n minus n plus r is, you see, minus 1 plus 3 is equal to 2. The others all have 2. So in a piece of paper, if you take a piece of paper and if you draw anything like dots, consisting of dots connected by lines, edges, okay, then you will get this number equals to 2. You can check it. It's very entertaining for starters, especially. It's one of the topological ideas. These are graphs on a torus. What is the difference? Difference is in the torus can be obtained by a piece of paper like this. You can just identify two opposite sides, okay, to obtain a cylinder like this. You obtain a cylinder, okay, and then if this was not a paper, it was a plastic, a stretchy plastic, then I could identify this circle with this circle here, okay? It would be like a donut, but I cannot do it with a paper, of course. It's not good enough for my purpose, okay? So, as I identified these two edges, you see, then this vertex will be the same vertex with this, okay? This vertex here will be the same vertex with this, okay? If you Google this, in YouTube, there are many ways how to obtain a torus from a square, for example. If you write this, you will find many illustrations, many nice videos. So the four corners are the same on these things, okay? So 2, 3, 4, 5, 6, 7 are different vertices, but there are 4 ones because they all are the same point on the torus, okay? And the right one, again, the same. What is common in those two graphs on a torus? N minus n plus r is this time equal to 0. Of course, 2 example is not enough to believe, but believe me, if you try any other things, you will get 0 again. So on the sphere or on the plane, it is 2. On the torus, it is 0. If you go to double torus, next one, it will be minus 2. Triple torus, minus 4. It will go like that. So, of course, Euler was a clever man, not too bad. He realized that any compact orientable surface S of genus G, genus is the number of holes in the sphere, genus is 0. On the torus, it has only one hole, so genus is 1. Double torus, genus is 2, okay? This number is invariant. So it's denoted by chi of the surface equal to n minus n plus r, and it's also well known that chi of S, this Euler characteristic, n minus n plus r, is also equal to 2 minus 2g. If you go back to examples, here genus is 0 for spherical graphs, planar graphs. So if you put g is 0 here, okay, you will get chi equal to 2, as we did in those examples. For the torus, genus is 1. Genus is 1 means chi of S equals to 2 minus 2, which is 0, as we obtained in both cases, okay? So that's a nice invariant known for more than 2 centuries now, and many topologists, many geometricians, many graph theorists, many people doing this kind of research have used this invariant. So luckily, we realized that there is another invariant like this, not maybe that much important at the moment, but it's actually because of its uses, many areas in many areas we can use it. So it is quite important, and in future I believe that it will be used by many people. So what is this omega invariant? I shall talk about this in my talk in the beginning, and at the end of my talk, I will be giving what I should say regarding to the title of my talk, the number sequences. Okay, I will give the Fibonacci graphs as an example. It will not be very long, but the omega part is more important. You must realize that it has lots of properties. I will try to give the most important properties in my talk. And as I said, if you need to remember this, you cannot remember them all, of course, during my talk. Even if you take notes, then I can send you the papers and my talk. All right. D is a degree sequence. What's a degree sequence? I mentioned before. Non-decreasing, non-negative integers. The set of non-decreasing, non-negative integers. There are, of course, zeros sometimes if you have isolated points, because the degree of the vertex, an isolated vertex would be 0. It has no connection with other vertices. But we don't like this, but we can extend our studies to, of course, anything. So capital delta is the largest degree in the graph. D1 is usually 1 if there are leaves, pendant edges like this, okay? G, if you can obtain a graph with the degree sequence equal to these numbers, then D is called realizable, and G is a realization of the set, okay? There are two problems. Given a degree sequence, can we obtain a graph? Can we realize it? There are many tests for that. Havel-Hakimi is the most well-known, okay, from 1950s, 1960s. It's an old test, actually. But how many realizations are there is not known yet. It's an open problem. You can try to solve it. Given a degree sequence, 1, 1, 2, 2, 3, 3, 4, for example. If it's realizable, then how many graphs we can draw having these vertex degrees? That's an open problem, very important problem in graph theory. Okay, for example, for this degree sequence, only once, 3 times 2, and 1 times 3, once 3. So you see this graph on the left has degrees 1, 2, 2, 2, 3. And the other one on the right, 1, 2, 2, 2, 3. The same set, okay, with multiplicities. So this set, we can say easily that this set is realizable in at least 2 ways, because we see 2 graphs with this degrees. So let's go now to mathematical parts. The motivation was that to obtain, luckily, of course, searching for something else, we realized, my student realized actually in 2018 that there is a nice relation. He didn't call it invariant at the beginning, of course, no one can do that. But after some months of insisting on me, he made me believe that it's an important relation, and we worked on it afterwards. Now we have lots of results on this omega. Okay, the number of leaves. What is a leaf? I said in the previous slide. It's a pendant edge, pendant vertex at the same time of degree 1. Okay, the endpoints of the tree. These are leaves, like the 3 leaves at the end, okay? The end point of the tree. The number of them is given by 2 plus A3, 2 times A4, 3 times A5, 4 times A6, plus capital delta, which was the largest vertex degree, minus 2 times A delta. Okay, this is a nice formula known in some textbooks of graph theory. What is A5, for example? A5 is the multiplicity of fives in the vertex set, in the degree set, okay? Degree sequence. This equation can be rearranged if you take A1 to the right and 2 to the left, okay? Then you get the equation 2. The left-hand side is important, so this is what we call omega invariant. It is equal to minus 2. We shall see that why it is minus 2. Okay, but for other kind of graphs, non-trees, it is not taking the value minus 2. It is being 0, 2, 6, 10, 12, like this, okay? Or minus 2, minus 4, minus 6, but always even numbers, we'll see. So, we defined, after realizing the importance of this set, actually at that time we were working only with molecular graphs, carbon graphs, where the degree, maximum degree is 4. You know, in a carbon graph, carbon molecules, carbon atoms have 4 chemical bonds with hydrogens or with other carbons or with some other elements, and there is no connection with more than 4 or 5 edges, you know. So this was much easier, okay, for the studies that we were doing at that time. Now we generalized it to any degree set. So this is a fixed number. This is the formula for omega. I minus 2 times AI. I from 1 to capital delta. So just to realize what is going on, omega is 14 for this graph. Why? Because there are 1, 2, 3, 4 pendant edges, you see, pendant vertices, or we can say. There are 3 vertices of degree 3. Here 1 and the other 2, okay? And for example, there is only 1 degree 5 vertex. Is this one? No. Oh, yes, here at the top. This is of degree 5. 1, 2, 3, 4, 5. The others are there as well. You can check them. Okay, this is the degree sequence of this given graph. For a given graph, you can easily calculate it, determine it. The omega is calculated as you start with 3. You don't see 1 and 2. We don't have 2 anyway here, but you don't take them into account at the beginning. You start always with 3. 3 times 3 minus 2. You remember the formula? Always minus 2. 3 times 3 minus 2, 1. 1 times 4 minus 2 is 2. 1 times 5 minus 2 is 3. 2 times 7 minus 2 is 5. Minus, actually it's not a minus. It is 4 times 1 minus 2. But it's always minus 1. Okay, so we take it as minus 1, like here, okay? Minus A1. But it's actually the same. They are all in the same summation. So you can write it as plus times minus. At the end, you will get minus. So if you calculate it, the number is 14. Why it is 14? What should we comment by this number? Okay, we shall see that. Of course, when you search for something in mathematics, you just start with observations. For young students, I'm telling this especially. My senior friends are knowing this, of course, naturally. If you observe some relation, if you observe some clustering, of something, some numbers, some functions, some sets, whatever it is, okay? Then you search for some special classes, okay? In our case, these are classes of graphs, of course. What are the most well-known classes? Paths, cycles, stars, complete graphs, complete bipartite graphs, trees, wheel graphs, friendship graphs, okay, this kind of things, ladder graphs. There are some more used graph classes, most commonly used graph classes. We searched some of them. You see, for cycle graph, it is 0. Similarly, for tadpole graph is something like this, okay? A cycle of any length together with a path as a tail, okay? It's like the tadpole. It's the animal, small animal, before becoming frog, you know, in the water. So for CN and for TRS, tadpole graph, it is 0. For path graph, for star graph, or for any tree in general, it is -2, interestingly, okay? So there are some clustering. So this gives you idea. For trees, whether for all trees we have -2, or are there some extra cases, different cases, okay? For all cyclic ones, is it 0, for example? So briefly, I will not go into the proofs. I have only time to mention about the idea. Omega is equal to 2 times m minus n. That's the first formula we obtained. 2 times m minus n. You can easily prove it by using the sum of the vertex degrees and the number of vertices. You can use them and you obtain this easily. So for any graph G, because of this theorem 3, omega must be therefore, if omega is, when you calculate it, if omega is, for example, 17, it's an odd number, then you can say that this set is not realizable, okay? So this is corollary 5. If omega is odd, it is not what we want, okay? It must be even, always. For a given graph, it is even naturally because it's already realized. But for a given set, if you calculate that omega is odd, yeah, you just throw it to the rubbish bin, okay? And another result is in Theorem 6, the necessary and sufficient condition for a simple connected planar graph to be a tree is omega equal to -2. We realized this in the examples about graph classes, remember? Another one is omega is additive. That means if you have 5 components, for example, you calculate each one, omega of each one, and you sum them up, okay? Then you get the complete graphs omega invariant, okay? And this theorem 8 is very important. Please try to remember this theorem. The number of faces is equal to omega divided by 2 plus the number of components. If it is connected graph, if you want it to be connected, then C is 1, okay? For example, in this graph, with omega equals to 14, the number of faces is, you see, is connected. 14 divided by 2 is 7, plus 1 is 8, okay? So this graph has 8 faces. You can count them, okay? There are 3 here. If there was a vertex here, there would be more, okay? But this is a square, one face. If you divide it by this, okay, then you get 2 triangles. Another dividing, so you get 3, not 4, okay? This is a complete graph. Because if you think of this line, if you think of this line, to be moved outside like this, okay, you delete this, okay, then you have one triangle here, another triangle down, and another triangle outside, okay? So we have 3 faces here, 4 faces, 5 faces, 6 faces, 7 faces, and 8 faces. You remember, in topology, we count outside because we deal with the surfaces, but in graph theory, we deal with concrete graphs. Outside is not important. Outside is endless, like the world. We don't care about outside. Some people do, of course, in NASA. Okay, so R is omega divided by 2 plus C, okay, which is 8, for example, for our case. For any graph G, we have C is greater than equal to minus omega G over 2, which is equal to M minus M. This is the lower bound for number of components. You can delete the 3 parts. You can calculate the omega of this one instead of this one because you just trim out these parts, okay? This is another result. As I mentioned in the first page, there are 3 cases. One is omega is greater than or equal to 0. The second is omega equal to -2. And third one is omega is less than or equal to -4. Everything goes in these classes, okay? So we gave some theorems for how to draw these realizations. If omega is 0, there is a special way. If omega is non-negative, there is a special way, and we have cyclic realizations, surely. If we have -2, omega equals to -2, then we obtain a caterpillar tree. A caterpillar tree is like this, okay? A special kind of tree with legs at maximum length 1, okay? All the vertices are in maximum distance 1 from a path. That's a caterpillar tree. So we gave the ways exactly how to construct as algorithms. So I have no time for this. And for example, with omega invariant, you can do this kind of calculations. I give you some examples. Is this degree sequence realizable, for example? What is the number of faces of a connected realization or a disconnected realization with 3 components? Someone asked you to draw a graph, disconnected graph, having 3 parts, okay, 3 components, with these vertex degrees. Is it possible, for example? Another problem. What is the number of maximum number of components? 3, 4, 5, 10, okay? Can we get a maximum number? Could it be connected, for example? So omega is 12. You can calculate it. You remember, once more I will do that. 3 times 1, 2 times 2, 1 times 3, 1 times 5, and 3 times 1 minus 2 minus 1. So we get 12 for this degree sequence. So it is even, that's a good thing. So this is realizable. You can draw it at least in one way, okay? By Theorem 8, about the number of faces, any connected realization will have, as it is 12, as it is non-negative, we say that there is at least one cyclic realization. So any connected realization will have cyclomatic numbers omega divided by 2 plus 1 equals to 7. So this is a cyclic connected realization. You see the number of faces: 1, 2, 3, 4, 5, 6, 7. Okay. Another realization: 1, 2, 3, 4, 5, 6, and 7, I think. Okay, so connected realizations will have 7 phases. You can count them. All right. And if you have disconnected with 3 components as asked, then you have 3 components. There are, of course, other ways you can form this. And this is of degree 4 vertex. This is another degree 4 vertex. There are 2 of them. This is degree 5. This is degree 7. Degree 1s, 3 of them. Degree 3, 1s, 3 of them, and 1 degree 2. Okay, so this all together give the same graph. Okay, not same graph, sorry, give another graphs with this degree sequence. I want to say. So when you increase the number of components, you get more cycles. Okay, you increased it from one piece to 3 pieces. You increased by 2. So the number of phases increased by 2 from 7 to 9. Okay. So if it was 3, it was going to be increasing 3 by 3. Okay. It's a nice relation. So what is the maximum number of components? So this is another problem. For example, we gave this formula. It's easy to deduce actually. The maximum number of components of any realization of D is C max equals to AI, where DI is even, plus the sum of AIs divided by 2 all over the vertices of degree odd. Okay? So, for example, for this degree sequence, 3 to the 4, 4 to the 2, 5 to the 2. Which degree is even? Only 4. Which degree or degrees are odd? 3. May have 4 components, or it may have 5 components, nothing more. Okay, that's very important, because once drawing, if you are using a computer to, for example, to prove something, then this kind of bounds are very important. Diophantine equation people, for example, do this. They use logarithms. They deduce the equation in lower terms, and by calculating the bounds, they just give the program. They just apply the program, and they get the solutions for some Diophantine equations, for example. Another problem, I don't have time, I think, for the another problems. I should go to my talk, but I shall say just one more thing before going to the final part. For example, we can obtain some new results on graphs, okay, by omega invariant, or sometimes, this is just an example, sometimes we can deduce some old problem, some old theorem, okay, in more easy terms by omega. For example, this potentially connectedness. Edmonds gave this theorem in 1964, 56, 57 years ago. Let D be a loops, and for 4 loops, and B are graphs. And there are two vertices. For example, one other hand. Okay. Also, we had this is for the T, having 9, 10, and 7 loops. And this is final one, we don't need more. Ten, 6, and 7 loops at each vertex, okay? So, having defined these graphs, we also use some private special notations. If you have, for example, a number, an integer, after some other integer in brackets, okay, then this means 3 loops are added to one of the vertices. B21 is this part, starting with this B2 and 1, you remember? Here, okay? So 3 means at the end of these 2, because it's after 2, we add 3 loops, okay? So there are some kind of notational conveniences we made. So there are some observations about Fibonacci numbers, you see. For example, what about evenness, oddness, the parity of the Fibonacci numbers? If the index is divisible by 3, then the number is even. Yes. You see, 2, the third one, 8, sixth one, 34 is ninth one, okay? The next one, 144, the 12th one. The others are all odd, okay? So every third one is even. So what we obtained, Fibonacci graphs of order 1 we searched for. What is Fibonacci graph of order 1? Order 1 means one vertex. You have one vertex and it must be, of course, if there is one, you don't need consecutive ones, okay? It must be Fibonacci graph because this is because of the handshaking lemma, isn't it? The total vertex degree must be even. That's the idea. So if you have one vertex, it must have even degree. So which Fibonacci numbers are even? Every third one. You remember? So F3K is the number of this number, okay? If you divide it by 2, you obtain the size, okay? The number of loops. So the graph is L. L means for loops. You remember the loop graphs? L of F3K over 2. This is the graph. So what is the omega for this? You calculate F3K minus 2. So all Fibonacci graphs of order 1 may have this number of faces. They may have 1 face, 4 faces, 17 faces, 72 faces, goes on, okay? And these graphs are these. So we showed that a graph with one vertex is a Fibonacci graph if and only if it has F3K over 2 faces or some positive K. So next, Fibonacci graphs of order 2, okay? Again, now we want graphs with 2 vertices and the vertex degrees must be consecutive Fibonacci numbers. 1 and 1, 1 and 2, 2 and 3, 3 and 5, 5 and 8. We go for all possible. We obtain that if R is congruent to 1 modulo 3, that is the degrees of the vertex for k, and if the graph is connected, then we have this result. A graph with two vertices is a Fibonacci graph if and only if its degree sequence is f3k plus 1, f3k plus 2 for some integers. So it goes on like this. We obtain the number of faces by means of omega invariant. We obtain the maximum number of components, in how many ways we can draw this. Okay, so everything we know. We have the catalog of all Fibonacci graphs. So these are, for example, examples. I couldn't give all of them, of course, here. These are examples of order 2 Fibonacci graphs. Because any three numbers you add get numbers. Any three consecutive numbers is realizable. So that means any three consecutive what is the maximum components here to you get pieces. Okay, there are to search for this is just omega is this number, the faces is 0. For the next one face is one, next one is only one face. You can go like this, all of them. And this I have to see are all the possible graphs. And finally, the general result. This one gives you in modular 3 and the general idea of omega invariant was introduced in Turkish Journal of Analysis and Number Theory now nearly 3 years ago. And this is second paper on the topic, external problems and on components and loops. These two especially are very important, and the rest, the other papers are the following properties. For example, next one is about cyclicness, maybe this one, for example, is about and the omega invariant, for example. And for example, this one is connectedness and omega invariant, for example. This is about topological indices and omega invariant, for example. This is omega invariant of line and total graphs. For example, you study with some graphs and you want to apply this, you can do. So, okay, I think I took more than I should do. Okay, I thank you and for listening. Mikkan Andrew.
Thank you, sir. Thank you so much. Thank you for your informative speech. And it's really pleasant to hear you wishing us in Tamil. Manamarna Nandri. Next, we move on to the technical session 2 of the day. Now, I call upon Dr. E. Prakash sir, Assistant Professor, PG and Department of Mathematics, at Arts and Science College, to welcome and introduce the speaker.
Good afternoon. I feel immense pleasure in introducing our honorable speaker, After industrial mathematics, 2006, he's serving Frankfurt. We are very grateful to Dr. Oliver Brady for accepting our making his presence here. Science knows no country. I wholeheartedly welcome you to this occasion and request him to take over the session and enlighten with his words on the topic applied mathematics examples from academia and industry. Thank you. Oliver, can you able to hear me?
Yes, I'm to hear you. Good morning. Thank you for the beautiful introduction, Prakash.
Yeah.
It's a pleasure to be with everyone. Good morning from Frankfurt, Germany. And good day to all of you over there. I've been able to listen a little bit to the previous presentation already. So thanks again for the I'd like to talk about mathematics. In this research presentation. So it is, I would like to express things are able to really work when you apply it from an application perspective. And I will present 2 examples from my past where I have worked with such things. And so that's really the thing I would like to express. So just to make sure, are you seeing my presentation slide? Is everything okay? Okay. Perfect. Then the agenda for this talk is I'll very briefly